be covering our last chapter for this semester on the mole. Very easy chapter, very math-based, critically important for this year. I think you will be very strong with it. It involves a tremendous amount of math. Learning goal: through inquiry and exploration, students will be able to convert quantities involving the mole. That's what we'll get into today. Calculate percent compositions from chemical formulas and the lab data that we're going to generate this week. And then finally next week we'll be determining empirical and molecular formulas, and that's very important in CSI types of scenarios, and we'll talk a little bit about that. This again is a very mathy chapter. You're going to need a calculator. If you want to borrow one, you're welcome to get it. My drawer is open and you can pull one. You'll also need a periodic table. If you can't find yours, there's a whole stack on the desktop. And we are going to learn today about the mole. And when you use the term mole, there are a lot of things that can come to mind. You can have little critters that look like rodents with 4 legs, like a big fat mouse. Or you could have a mole as a birthmark or a beauty mark on somebody's body. A lot of different ways that you can think about the mole. But in chemistry, the mole is very important because it allows chemists to relate different substances with one another. It's a way to compare iron with magnesium, with carbon dioxide, with glucose. So you can make a comparison of a lot of different substances. And this little video is very cute and starts to describe the mole.
Somebody might be thinking that it's the growth on your ant's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, just about anything extremely small. Have you ever wondered how many atoms there are in the universe or in your body, or even a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you had equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to sign autographs. Fortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Fortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container, or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 septillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, you probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd. Not a fuzzy little animal. The only difference is the other quantities are more familiar to us. So there you have it, the story of the mole. Avogadro, basketballs, and how to buy salami at the grocery store.
I really like that video because it makes excellent comparisons between the mole, the dozen, a ream. Many of you probably haven't heard of a gross. If I had heard of a gross because we used to order certain things from my dad's store, and that's where the gross came in. But otherwise, I'm sure most of you have heard about a dozen. It doesn't matter if you have a dozen students, a dozen eggs, a dozen cookies, a dozen bagels. You always have 12. So it's a nice way to compare different substances. And the mole is really very, very similar. A mole contains as many elementary entities as there are atoms in exactly 12 grams of carbon-12. And if you look at a periodic table, you know that the atomic mass of carbon is 12.011 AMU. And carbon-12 is the standard by which everything is based. When you talk about elementary entities, this is a little bit tricky. We're going to walk through this very carefully. And I'll show you the elementary entities in elements, diatomic elements, covalent compounds, and ionic compounds in just a minute. They showed you why the mole is needed. The atom is very, very small. To assist in counting them in a much simpler way, chemists have come up with a unit known as the mole, and that's going to represent how many particles are in a given substance. And 1 mole of anything is equal to 6.022 times 10 to the 23rd particles, atoms, molecules, etc. And let me show you what these elementary entities represent or go with on a simpler scale. Let's say, for example, that you had 1 mole of carbon. That's going to be equal to 6.02 times 10 to the 23rd. If you have an element your simplest entity will be the atom. If, for example, you had a diatomic element, that's also equal to Avogadro's constant, but now you're going to have molecules. And if you have 1 mole of a covalent substance, such as carbon dioxide, this is going to be 6.02 times 10 to the 23rd molecules as well. And remember, for covalent compounds, you're going to have 2 or more nonmetals that share electrons between them. And look for that in your project. Make sure your covalent compounds only have nonmetals. Your covalent compounds can have polyatomic ions if they link to hydrogen. Be careful there. I'm seeing a couple of mistakes as kids have shown me some of their selections. And then finally, if you have 1 mole of sodium phosphite, this too is equal to Avogadro's constant, with the only difference being the elementary entity. In this case will be particles for an ionic compound. And so we have a whole series of equivalencies here. It's really the same equivalency for elements, diatomic elements, covalent compounds, and ionic compounds. And for an ionic compound for your project as well, make sure you've got a metal in there. That'll really help you. Those should be the easiest to find. So 1 mole of anything is equal to Avogadro's constant. This is an equivalency that you can easily establish, and once you've established this equivalency, you can use it to make simple conversions. Questions on this equivalency where 1 mole of anything is equal to Avogadro's constant. The only difference is the unit right here. For an element, you're going to have atoms. For a diatomic element or a covalent compound, you'll have molecules. For an ionic compound, you'll have particles. Okay, we're going to do some simple conversions, and you've already done these this year, so I don't think you will find them terribly difficult. Again, you really want to be meticulous in your setup, and I want it set up in a certain way that you can follow and that will lead to great success as we work through chemistry this year, not only with these simple conversions, but more importantly with the complex ones. And so you'll see there's a specific way I want it set up, and there's a specific way that you're going to set up your fractions, and I'll point that out to you. In the first problem, it says how many atoms of sodium? That's what we're trying to find, hence the question mark. That's the unknown. Are equivalent to 3.7 moles of sodium. That's my given. I have a number, a unit, and a substance. And if you think about this, you're always going to have 3 pieces, a number, a unit, and a substance, and that will help you tremendously in your setup. That's my given. That's what I start with. In red is my unknown. That's what I'm figuring out. I always start with my given. I'm going to rewrite these first 2 out very slowly so you can see how they're derived. You don't need to rewrite them. You can just watch. You have them in your notes. In the first example, I'm given 3.7 moles of sodium, and what I want to figure out is atoms of sodium. If you're ever given moles or asked for moles, it will be a one-step problem for this type of setup. So you're given moles, it's going to be a one-step problem. I know that 1 mole of anything is equal to Avogadro's constant. Right, that's not a negative. I have a mark on the page. Is that clear? Not clear? I'll fix it. So that's a positive exponent. So that's my equivalency, and the only thing I need to do is figure out what goes where. My unit here is moles of sodium, so that means I need moles of sodium here. The number before moles for this chapter will always be 1. Avogadro's constant is going in the numerator. That's what I want to get to. And you will notice that I always have a number, a unit, a substance. A number, a unit, a substance. A number, a unit, a substance. That's important. If you're missing anything, I'm just going to put a dot on your page. And as many dots as I've made is how many points I take off. Be very careful here. Critically important that you have really good skills in your setup. And again, if anybody needs to borrow a calculator, please come pick one up. I'm just going to multiply those two numerators, 3.7 times 6.02 EE23. And I'm going to have 2 sig figs is 2.2 times 10 to the 24 atoms of sodium. Again, make sure those units cancel. You're getting to the unit you want. Also, we haven't played with the calculators for a while. Maybe redo this one so you can see in your calculator 3.7 times 6.02 EE or EXP 23 equals. Now, if you have the multi-view, it's a little bit different with yours sometimes, so we'll have to be careful with those. So if you have those, if you're having calculation errors, please let me know and we'll fix that. So make sure you're getting that one. Yes, yes? Awesome. On number 2, it says how many moles of xenon? So in number 2, we're looking for moles of xenon, and we want to know how many moles of xenon are equivalent to 5.66 times 10 to the 26 atoms of xenon. Now we know that 1 mole of anything is equal to Avogadro's constant. And again, this is something that we touched upon at the beginning of the year, so it shouldn't look foreign to you. You just need to make sure you're setting up the factor label method properly. You've got atoms of xenon here. So which quantity goes in the denominator of that fraction? Avogadro's constant, so that the atoms of xenon will cancel. And then 1 mole goes on top. Now this is like one big fraction, so you're essentially going to divide this by that. Make sure your answer makes sense as well. You have 10 to the 26th divided by 10 to the 23rd. When you divide exponents, you subtract them. So this should be in the 10 to 2 or 10 to the 3rd range. Be careful there. If you look at your quantities, you'll have a much better inkling as to whether you set the problem up properly. 3 sig figs is going to be 940 moles. Or you could use scientific notation if you prefer. Whatever rocks your world is fine. Three, how many moles of carbon are equivalent to 3.66 times 10 to the 22nd atoms of carbon? So number 3 is on the screen, and I'd like you to try number 3. Yeah, go ahead. See if you got what I got. Did you get what I got? And again, watch the unit cancellation. How'd we do? Piece of cake? Yes, yes? Good. And we're going to get some more practice with that. The other way you can link the mole to substances is right through the periodic table. And this way is going to be far more helpful to you. We're going to relate moles to grams. When you do labs, you very often mass out your substance using a balance, and you get a quantity with the unit in grams. You want to be able to relate different substances together, which you do through the mole. So there has to be a way to relate mass in grams to moles. Molar mass is defined as the mass in grams of 1 mole of an element being numerically equal to the atomic mass of the element, which of course can be found on the periodic table. So if you were to look at a periodic table, for example, carbon. Carbon has an atomic mass of 12.011 AMU. Instead of AMU, we can replace AMU with grams per mole. That is, 1 mole of carbon is equal to 12.011 grams of carbon. We can generate an equivalency. We had sodium, for example. Sodium's atomic mass is 22.990 AMU, or we could say 22.990 grams per mole, or 1 mole of sodium is equal to 22.990 grams of sodium. So from the periodic table, we can change AMU to grams per mole, and then we can make equivalencies. 1 mole of any substance is equal to its mass in grams. Once we make these equalities, we can do simple conversions. And that's what we're going to look at here in 1 through 4. So in number 1, it says how many moles of carbon are equivalent to 22.5 grams of carbon. We want to know moles of carbon, and our given is 22.5 grams of carbon. Same setup with given and unknown as we saw previously. Start with your given, which is 22.5 grams of carbon, and we want to know how many moles of carbon are equivalent. We know that 1 mole of anything is equal to its mass in grams. 1 mole of any substance is equal to its mass in grams. If I have grams of carbon here, I'm going to have grams of carbon here. Don't divorce a quantity. 1 mole of carbon here. That allows me to cancel what I started with the denominator of the first fraction. This is like one big fraction, and I have 22.5 divided by 12.011, and that's going to be equal to 1.87 moles of carbon. And again, you may need to go back and review sig fig rules. You have 3 sig figs here. Whatever I'm given in these types of factor label method problems, I'm going to give back at the end 3 sig figs. Questions on the first problem? It's clear what you put where and why? All right, in number 2, it says how many moles of sodium. So I'm looking for moles of sodium. I'm given 50.1 grams of sodium. What am I going to do? Okay. So 1 mole of sodium is equal to what mass in grams? It's right in your notes. Alrighty, and what's going to go where?
The 22.99 idea for going bottom.
How come?
Because like the units cancel out.
You got it. Perfect.
And then one more is going to go on top.
And then you plug and chug away. 50.1 divided by 22.99. And that's going to be 2.18. 3 sig figs. Easy peasy. Let's do one more together. I'll let you try one, and then I'll show you one of the double fraction, and you'll be ready to practice. Number 3 says what mass of calcium in grams is equivalent to 0.750 moles of calcium? What's my given? What's my given in number 3?
0.75 moles of calcium.
You got it. So that's what I'm going to start with. Your given has to be a quantity. Oh, I'm sorry, moles. And what do I want to get to?
The mass of calcium.
All right, so the mass in grams. So what do I do? Luke, what goes where?
Moles, or 1 mole of calcium on the bottom, and 40.078 grams of calcium.
Now, your periodic table says 08, so I'm going to keep it there. You have one online. I'm just going to keep it simple. Either one is fine. How come you put the moles in the denominator?
So it cancels out with the given.
You got it. So 3/4 of this should be 30.1 grams. Yes, yes? Easy, easy? You try number 4. It's on the screen. What'd you get? What'd you get? Piece of cake, huh? If you're given moles or asked for moles, it's going to be a one-step problem in this chapter. Very straightforward. The last thing we want to look at is going through the mole. So you can be given the mass in grams and want atoms, or you can be given atoms and want the mass in grams. So if the atom is given or asked for, but it sets up against grams, that is the mass in grams, you're going to need multiple steps. So we're going to do 2 easy conversions from mass in grams to atoms, or atoms to mass in grams. Either way, you're going to go through them all. These are going to be 2-step problems. Now, I don't like to memorize how many steps things are because it really can vary. In this chapter, I will say if you're given moles or asked for moles, then it will be one step. Otherwise, it's going to be more than one. In number 5, it says, what mass in grams of strontium? That's what we're looking for. Is equivalent to 3.50 times 10 to the 22nd atoms of strontium. These types of problems are multi-step problems, and I very often will write sideways on the page because it's going to be multiple steps and it may be easier to follow. So in this problem, we're given 3.5 times 10 to the 22nd atoms of strontium. And we want to get to the mass in grams. We're not given or asked for moles. This is going to be a multi-step problem. It's going to be 2 steps. The first thing I need to do is get rid of atoms of strontium. You don't need that of sign there. I'll take it out if it'll bother you. So if I have atoms of strontium here, what number always goes with atoms? Avogadro's constant. And that is provided to you on the back of your periodic table. You don't need to memorize that. On your periodic table, it's in the box right there. That is a constant that is provided. And what quantity always goes in the fraction against atoms or against grams? 1 mole of it. So that will allow you to cancel atoms of strontium. Now you're going from moles to grams, and this is what we just did. 1 mole of anything is equal to I think that's right. Yes, yes? Yeah. Off the periodic table. So again, the grams is coming off the periodic table. I like to treat this as one big fraction. I multiply the numerators, I hit equals, and I divide by the denominator. So I have 3.5 EE22 times 87.62 equals divided by 6.02 EE23, and I have 5.09 grams of strontium. And again, if moles are not given or asked for, it's going to be a multi-step problem. Go from atoms to moles, and then moles to grams. And on your quiz, I'm always going to be looking for 3 things everywhere: the number, the unit, the substance. The number, the unit, the substance. The number, the unit, the substance, etc. Let's set up 6 and let's see if you can process it. On number 6, we want to know atoms of barium equivalent to 150 grams of barium. What do we do? What do we do? What do we do? Always let your units drive you. If you have grams of barium here, what goes in the denominator of the first fraction? And grams comes off of the And what goes against the gram? 1 mole. Now we got to go moles to atoms. So if we have 1 mole of barium here, what's going in the denominator? And what goes in the numerator if we want this unit? You got it. Multiply the numerators, hit equals, divide by the denominator. What'd you get? Did you get what I got? Yes, yes? Cool. Not difficult. Take some practice. I'm going to give you your classwork, and you can do 1 through 12. You'll get a little bit of it done today. I really recommend that you do it for tomorrow. Tomorrow we'll have a new lesson. Wednesday is probably going to be a problem-solving day for your class, and that way I'll be sure that you're really understanding. Questions here? All right, so we're getting a basis of the mole. The mole is a way that chemists can compare substances. You've got an equality that 1 mole of anything is equal to the mass in grams off the periodic table. That's known as molar mass. And the other equality we established today is the one with Avogadro's constant. And that is that 1 mole of anything is equal to 6.02 times 10 to the 23rd. And that can be atoms, particles, or molecules as we discussed previously. This chapter is really, really important for success in chemistry. I think it will be a relatively easy chapter for you because it's so math-based and you're so strong in math, but it really does require practice. On your classwork, 2.4, you can now do 1 through 12. I would say if you can get 1 through 8 done for tomorrow for your class, since I see you again tomorrow, I don't see the other kids until Wednesday. If you can get 1 through 8 done, I would think you could get 1 through 5 done before you walk out the door. I would do it on a separate sheet of paper so you can identify your work. And if you're struggling with your calculator, please let me know. I will help you fix that.